Okay, so we're going to just continue the same sort of theme and just do further exercises to shore up your understanding. If you're doing, think about your own study that you want to do, and you want to compute power and get an idea of what sample size you might need to demonstrate an effect. You can just use those Cohen's lookup tables that I showed you, but there's also a free online computer known as G-Power, which handles quite a wide range of designs. That's also, a lot of people do use that. G-Power, though, does become challenging if you don't understand all the options and if you've got a rather more complicated design than, say, a sort of simple two-group comparison. I would say the best way is to use simulation. So this ensures that you understand enough about your data to simulate it, and it can actually handle any degree of complexity you throw at it, because basically you just are running the analysis that you would run, but you're doing it many times on simulated data to check out how often it reveals the effect you're interested in. The big problem that people have when they start to try and do a power analysis is deciding what effect size to choose. How do you know what sort of size of effect you might expect to find? In the past, people would say, well, you look in the literature, what sort of effect sizes other people have found. It's now recognized that that's very likely to overestimate effect size because of publication bias. That is, people are much more likely to publish significant than non-significant findings. And so you get an inflated idea of how large effects are. And in general, I think these days people are saying it's probably better to actually think about what would be the smallest effect size you'd actually be interested in. If you study 1 million people, you will be able to detect effects that are minute. But are they of any interest? Are they of any practical significance? There comes a point when you want to say you have to think about whether it's worth the effort to collect more data to detect effects that are really tiny, and not going to matter. So if you're doing something like a clinical trial, I think it sometimes is easier to anchor this in reality, because you might be measuring something like the effects of a drug on whether people get migraines. And you can actually think about, what reduction in migraine rate would actually be clinically valuable. If you had recruited people who are having sort of, 4 or more a month, if you got them down to 3 a month, that probably most people with migraines would say that would be valuable. If you move, though, from 4 to sort of 3.9, maybe not. So you can try and think about your original scale of whatever you're measuring on, and have a think about what would be a sort of interesting and useful effect. But sometimes that's quite difficult if you're working in areas where it's not really known. So it can be sensible to look at what do different effect sizes look like. And people are often quite shocked to see, when you plot them as overlapping distributions, how tiny a lot of effect sizes are that we regularly operate with. Certainly in psychology, people studying things like sex differences in personality, effect sizes are 0.2, 0.3. And what you can see here is that means that there's really a shift in the mean between these two distributions, but a substantial overlap as well. If you look at educational interventions, the effect sizes, you're lucky to get one of about 0.4. And a lot of clinical treatments, that's also true. Whereas if you take sex differences in height, you're talking about an effect size of 1.7, a massive, great thing, much more like the one at the bottom there, still with overlap between distributions, but the means are really quite clearly separated. So this is useful to get. Often, I mean, I worked for years and years with effect sizes without having visualized them this way. And I have to say, I was quite shocked when I realized how much overlap there is in distributions when you're talking about the sort of effect sizes we usually work with. I'm going to suggest that we look at a package called simstudy, which is one of the many packages available for simulating data, just so that we experience a different way of doing things. And I'll come out of PowerPoint and show you the script, which we need to walk through just to give you an idea of what's going on in it. So this script is this one here. It's called simstudy power demo. And you might need to install the package called simstudy. if you just run this script, this is a way of getting it to automatically install it if it finds it's not there, which you can do. Some people don't like that. They regard it as allowing too much control to the script of what goes onto your machine. So it's slightly more difficult to decode what's going on in simstudy than in the little programs I did on, I've got an open science framework, but it is very much more versatile. And so it's worth sort of at least introducing you to it. Let's say we're going to have an effect size of 0.3. Now, this time I'm going to say we're going to define our scores not as z-scores, but we're going to define them so that the group difference is a raw score of 1 on some sort of scale. It might be number of headaches or something per month. So if we want an effect size of 0.3, we actually then have to work out what would the variance be to give us an effect size of 0.3 if our raw score difference is 1. This is where it gets a bit convoluted. But I'll show you as we go through the script how this works out. But basically, you need to specify the variance as 1 over the effect size squared, and that will give you that effect size of 0.3 when the mean difference is 1, if you've got that much variance. It'll come clear, I hope, as we go through. And then this is the way simstudy works. It has a function called def data, define your data, which will create a data frame with the variables in it. So we have a variable called group. This is binary, that is, it's either 1 or 2 or 0 or 1, and it's set to be 50% in one group and 50% in the other. You'll see when we look at this data frame that you haven't got all the noughts at the top and the ones at the bottom. It's like for each new data point that's generated, it applies this formula, which just randomly selects a 0 or a 1. I think it's probably 1 and 2 rather than 0 and 1. But, and then you have to define your treatment variables. And we want to specify the error variance. So you're going to say the score that you observe is the sum of the true score, the group score, and the error variance. So here we are. This is this variance we specified up there to get the effect size we wanted. And then we have the score, which is just then the group score plus the error variance. So the groups are 1 and 2. So this is a simple way of ensuring you have a group difference between the two groups on score of averaging out at 1. Let's say a little convoluted, it might do your head in thinking about it. Don't worry if this seems difficult. But we're then going to create a giant population of 10,000 with those settings. And again, gen data here is the way simstudy does it. It says take these variables we've specified and generate some data. And we're calling it my treat. It's saying my treat vase isn't found. That's because I didn't run that bit. So let's run that bit. In fact, that's right. I'm not sure when I started to run this. I was just talking about it and not running it. So let me run all of this or we'll get into trouble. There we go. And then we should have my treat now being created. Yes. So here's my treat. And what you see is that it automatically gives an incrementing ID. And then we specified group to be 50% noughts and ones. The error term here is showing you it's just a thing with the distribution that we specified as my var. And then the score you end up with will be the sum of the group identity and the error. This is just a way of ensuring a group difference in score between groups 0 and 1 of averaging out at 1. Okay. Now we want to check that this has done what we think it should have done. So let's do a little pirate plot. And that's our simulated data. Let me just move the screen so it's a bit more visible. And you see the group difference is 1. It's averaging out. And then here's the spread with this, based on this variance. And then we can check the means. So run these lines and the standard deviations for the two groups. So this is a way of making sure that it's taking the mean just from either group 1 or group 2. So it's saying take score values, but only select those rows where group is 0 or group is 1. So if we now have M1, M2, we've got a different, so the mean difference is very close to 1. It's not exactly 1 because of sampling error. You can see that it's virtually 1. And then if we take S1 and S2, the standard deviations are about 3 or 3.3. And so this range here, in fact, between 0 and 3, you've got, that means you'll have about 2/3 of the data in that range. And the observed effect size should be around 0.3. Let's see what it is. It's just above 0.3, 0.32. So that's our big simulated population. And then we're going to run through comparing sample size of 30 and a sample size of 100. We just do 1,000 runs, alpha level of 0.05. I've put a little toggle in here. If you want to make a PDF, you just change that to 1. And instead of outputting the data over here, it will then output it on a PDF, just as we did actually previously with that other script we were running where we were looking at those pirate plots. But for the moment, I'm going to just let it plot over here on the pane. So I've set make PDF to 0. So this just means that you don't run these commands to create the PDF details, or you don't set it up if you set make PDF to 0. Let's, yeah, we've got that far. Let's just try running this then. And it thinks about it a bit because it's running through this, doing this simulation 1,000 times. It's done it for 30 per group, and now it's done it for 100 per group. That's all a bit bunched up. That's one reason to PDF can be preferable. You can see it more easily, but you can see that what you've got here is power of about 0.25 when you've got 30 per group. That means that this is the proportion of these p-values that is less than 0.05. That's our alpha level. And it's not impressive. I mean, this is going to mean that if you had 30 per group and an effect size of 0.3, you're more likely than not to see the effect of interest. If you've got 100 per group, it gets better, but you've still got power of only 0.637. So again, that's still rather unsatisfactory if it would mean that in every 1 out of 3 experiments you ran, you missed an effect of interest. So let me return to my PowerPoint. And this is just showing you those outcomes. I in fact put these in blue. These are the ones that you would typically regard as significant. You can compare these power estimates with the ones from Cohen's tables, and you'll find they broadly agree. In order to get complete agreement, you have to run hundreds of thousands of simulations, and then they converge very, very nicely. These are worked out just mathematically, but simulation should give you the same answer and gives you a bit more insight into how it works. So I'm going to suggest that you have a play with the script and compare different effect sizes and sample sizes, and you might also like to download GPower and see what that does. I would say this is absolutely key part of this course to get you to have this intuitive understanding of how important sample size is. And I will aim to do something, if this makes you very depressed, I will aim to hopefully overcome some of that gloom as we go forward and see what do you do about it if you're grievously underpowered.